Let's talk about concavity. When we go to talk about functions, it's often the case that the first derivative is not enough. Take, for instance, this example of virus spread. So we have two different cases that have the same derivative. So the slope of the tangent line is not exactly at the same point, but those are the exact same slopes of those tangent lines. But as you can see, the situation is very different. So if at a certain time t, we were to just take the slopes of those tangent lines, and those are actually two different times, but if we were to just look at the slope of the tangent line, we would say these are essentially the same case, right? The virus is increasing. But these are increasing in very different ways, right? Which situation would you say is worse, and which would you say is better? In the case of virus spread, the first situation is much worse, right? Because it's exponentially increasing, even though the slope at an instant is the same as the second case, where we have a virus that's going up but leveling off. So what all this says is we need more than the first derivative, and it turns out that the second derivative is what tells us about the shape of the graph in terms of how it's increasing or how it's decreasing. And we call this phenomenon concavity. You can kind of think of these like a bowl, and when the bowl opens up, we say that it's concave up, and when the bowl opens down, we say that it's concave down. It turns out that the concave up case has a second derivative greater than 0, or positive, and the concave down case has a second derivative less than 0, or negative. So we can essentially determine analytically how these graphs would look without even having to see the graphs, as long as we have an expression for the function to begin with. Let's consider another situation with similar graphs. Let's consider the case of two different cars traveling from one stoplight to another. So they're at rest at a stoplight. Stoplight turns green and they travel, they start going, and then at the second stoplight they stop. So they're essentially both going the same distance. We start from point 1, we end at point 2. Second car starts at point 1, we end at point 2. One of these cars is a hot rodder, perhaps spooking everyone and giving the passenger a terrifying and thrilling ride. The other one is a grocery getter, just trying to get by on a Tuesday afternoon, taking a nice leisurely trip. Which one is which? It turns out that the first graph is the grocery getter and the second graph is the hot rodder. Why? Well, as the light turns green, the hot rodder hits the gas, so in a very short amount of time, right, they've gone most of the distance. They go boom, hit the gas, and they're going fast, quickly, and then they kind of chill out because they eventually have to stop because the light's going to turn red again at the next light. So this experience is boom, light turns green, and they hits the gas hard, and you go a long distance in a short amount of time. The grocery getter, the light turns green, and they slowly start to go, right? Everyone else is kind of passing them, and then they get their speed up, and then finally in the time for the next light, their speed is up, but it's time to stop anyway. So, two very different experiences, but if we just talked about velocity at any given time, it's not going to give us the complete story. We need to look at how these curves are shaped, and again we have our same idea of concave up and concave down. Right? You see this all over the place, right? Stocks. Two different companies can have stock that's increasing, but if one is concave up, that's going to be worth a lot more than one that's concave down. If your stock price is increasing but it's concave down, people are going to have concerns, right, that it's not growing fast enough and it's cooling off and all these things are happening even though the stock price is going up. So let's examine this concavity phenomenon deeply so we can pull all the information possible out of these functions as we analyze them. Okay, just to summarize, when our graph is somewhat the shape of a bowl opening up, though oftentimes it's not bowl-shaped at all, but just that kind of curve opening up, we say that that is concave up, and analytically it has a second derivative greater than 0. And similarly, when it's kind of a bowl-shaped-ish opening down, we say that that function is concave down, and analytically it has a second derivative less than 0. One more thing. The point at which a function changes between two different concavities is called an inflection point. So we can see here in this example that it's concave down, but then it switches, and right at that point it suddenly is concave up. So an inflection point is an xy value, so we do want to have the y value there. It's an actual point versus the critical points, which we've been taking as just the x values. Okay, let's look at an example. Find where the function is concave up and concave down, and identify inflection points, and then we're given the function f of x equals 2x squared natural log x minus 5x squared. Okay, well, there are some steps to go about doing this. Step 1, find the second derivative of f of x. So we're looking for f double prime of x. Okay, well, we can do that. We start by finding the first derivative. So let's make the f prime of x. Well, we have a product here, 2x squared and natural log x, so we'll hit that with the product rule. A prime b plus b prime a. So 4x times natural log x, that's a prime b, plus b prime a. Derivative of natural log x is 1 over x times a, which is 2x squared. All right, minus the derivative of 5x squared is 10x. Okay, well, we can clean this up a little bit. Note that this middle term is simply 2x. 2x minus 10x is then 8x, leaving us with a first derivative of 4x natural log x minus 8x. Okay, so we can now take the derivative of that, which will give us our second derivative. So then f double prime of x is, all right, we're back with another product. We have 4x times natural log x. Hit it with the product rule. A prime b, so 4 natural log x, plus b prime 1 over x, a times 4x, minus the derivative of 8x is, of course, 8. And we can do a little more simplification here. Note that the middle term is simply 4. So we really have 4 natural log x minus 4. Okay, on to step 2. We identify the possible inflection points, and those are the points where the second derivative either equals 0 or it's undefined. And then we'll use those to define our regions, and then we'll check our regions in step 3. Very similar to what we did with increasing and decreasing when we were just looking at the first derivative. Here's one thing that's strange and slightly annoying is this possible word here. When we're doing the second derivative and talking about inflection points, it only becomes an inflection point if the graph changes concavity. If the graph doesn't change concavity, if the function doesn't change concavity, then the point that we find is actually not an inflection point. Versus the first derivative, where it was a critical point no matter what, here it's only an inflection point if it happens to change concavity at that point. So some somewhat inconsistent vocabulary with this, but that's just how it is. Okay, let's look at where this thing equals 0. How about we factor out a 4? We get natural log x minus 1 equals 0. So we're really looking at where natural log x equals 1. How do we solve something with natural log in it? Well, there's a few ways, but I like to take both sides base e. E and the natural log undo each other because they're inverse functions, leaving us with x equals e to the 1, which is e. So here is our possible, at least the x value of our possible inflection point. Remember, the inflection points need an x and a y value, but let's just focus on the x values for now, and we'll do a sign chart. Okay, so just as a placeholder, we have 0 here, and then our main boundary is defined by e. Note that the function is not defined anywhere to the left of 0 at all because of the domain of natural log to begin with. So we're limited already. So we just need to do a test point between 0 and e. How about x equals 1? Recall that e is 2.7 something. So we can get to the left of it with x equals 1, and we can get to the right of it with x equals 3. Okay, and then let's test those regions with our sign chart. And just like before, we're only testing for positive and negative. We don't need to know what these values are. All we need to know is if it's positive or negative. What are we plugging in here? Well, we have 1 and 3. Well, depending upon how much you know about natural log, you can do this in your head. But if you're not entirely familiar with natural log, you may want to break out a calculator. But it turns out that when we plug in 1 for natural log here, we'll get negative. And when we plug in 3, we'll get positive. Because natural log switches from being less than 1 to being greater than 1 at x equals e. So you can kind of reason your way through that, or simply plug it into a calculator if you're not entirely comfortable yet. So that gives us a negative here and a positive over here. Okay, and now we can identify our regions of concave up and concave down. Okay, so where is this thing concave up? Well, where this is positive, where the second derivative is positive. So that's from e to infinity. E to infinity, and we never include the boundary points because at that point it is neither concave up nor down. So it's always an open bracket when we're doing these integrals. Concave down similarly is 0 to e because we only want to include the regions where the function is defined. So it's not negative infinity to e, it's 0 to e. And then our inflection point. Well, we know what the x value is, it's e, but an inflection point needs to have an x and a y value. So where do we plug in the x value to determine the y value? We have multiple options. We could plug it into f double prime, we could plug it into f prime, we could plug it into the original function, and that is indeed where we want to plug in. Anytime you want to get a y value, and this will happen a lot as we go through. Okay, so plugging into the original function to get a y value, let's see, so f of e is what? 2e squared natural log e minus 5e squared. Well, natural log e is 1, so it's 2e squared minus 5e squared minus 3e squared. So there's our y value. And we just plug this in down below. Let's clear out a little more space. Negative 3e squared for the y value. And you don't want to be throwing around a bunch of decimals, right? When you can have something as nice of an answer as e, you want to definitely keep it in e form. So there we have it, the regions in which is concave up, concave down, and our inflection point.